let me share my screen. Okay, and okay, can you see my screen and can you hear me well? Great, perfect. So hi everybody, my name is Robin Kipps. I'm working for L'Oréal Research and Innovation, and I'm also a PhD candidate at Telecom Paris, and this work is in collaboration with Modiface. So I'm going to talk to you about makeup synthesis, and in particular, I'm interested about makeup synthesis from example. So it's a simple task. It's a task in which what we want to do is that we have an example image with person A wearing lipstick and another source image with person B without makeup. And the objective of the task is to estimate the rendering of person B wearing the same lipstick or makeup as person A. So there is a lot of work in this, and in particular, it's a task that's regularly represented at CVPR. And all of the existing methods, usually they rely on the same general principle. That is, we take the reference image, which train an encoder model that try to extract the makeup appearance and encode it into a latent space. And then we also train a generative models that takes two inputs, the makeup from the latent space and the source image, and try to render the estimator of the makeup. And actually, a lot of different papers managed to reach nice results for this task. You have a few examples here. But if you want to push to production this kind of technologies, you start to meet a few limitations. The first one is that it's not really possible to use it in real time on portable devices, because again, if you want to do this in high resolution, the models are really big, so they are difficult to deploy. And also, there are some temporal stability issues for videos that you probably know if you work with GANs. And also, you are highly dependent on the training data distribution, so it might also create some problems later. You will see that later on. So the inspiration that we have for this work is to actually try to build upon existing augmented reality makeup renderers. So makeup rendering is actually a popular application of augmented reality. So you might have seen the images like this on the web store of existing makeup. And you can see that these technologies, which are based on computer graphics, they are able to do nice renderings in real time in limited setting, in the limited constraints of a mobile phone. So if we take a deep dive, a bit closer look to an example of computer graphics renderer, of augmented reality renderer for makeup. So it looks like this. Actually, have multiple blocks. Generally, it's a pipeline with some perception module. So in this case of lipstick, you take a deep learning network to estimate the lip mesh and the illuminance. And then you have a computer graphics renderer that computes the rendering, and then the rendering is blended on the render frame to get a nice realistic result. And what I want to draw your attention on is actually this little green box here, the lipstick parameters. Actually, there are a set of parameters that are used to control the appearance of the makeup that we want to synthesize. So for instance, for this lipstick example, you would have a parameter representing the makeup opacity, you would have an RGB tuple, you would have the gloss intensity and roughness, all kind of parameters. And it's actually really interesting space to work on compared to the learned latent space, because it's really compact. And I think by now you can kind of understand where this is going. So the idea that we propose is to create a deep inverse graphics encoder. So basically, we want to train this inverse graphics encoder here that takes as input the reference image and then estimates the graphics parameters that, when passed to a computer graphics renderer, will allow to synthesize a makeup with the same appearance. And one of the advantages of this is that since for inference you are using the computer graphics renderer, you are actually able to run it on video in real time and on a mobile device, and which is a great advantage compared to the other methods. So how do we train this encoder? Actually, it's fairly simple. We propose to do that using a self-supervised training procedure. So we sample a random graphics vector, so random color, random shine level. We feed that to the renderer together with a random portrait image. So these are images from the FFH dataset. And then you get the rendered image. And you pass this image to your encoder model, and you ask it to estimate the original graphics encoder that was used to create the synthetic image. So you can actually use a very simple loss in the space of parameters. So we use a L2 loss in this case, yes, and really that's it. So what's interesting here is that actually you don't need any kind of label data. You just need some random portrait images, and you need to be sampling some graphics. You also don't need a differentiable rendering engine because compared to other inverse graphics approach, we don't use a feedback loop in the image space. And this is actually quite helpful because re-implementing all your renderers in a differentiable way can be a bit complicated. And also what's interesting is that we actually fully control the distribution of G. So you can actually sample your graphics vector to make sure that your encoder see a lot of different colors, and it can even be more complex than reality. And you will see that in terms of robustness to extreme examples, it's really interesting. Okay, so now a few results. You can see that so we extract the lipstick appearance from this image, and we synthesize on this image, reaching this result. And you can see that we managed to extract the right color, the right level of shine. So this is a dark red, which is quite matte, and this is more nude and shiny lipstick. And you can see that we managed to reach results in a high resolution. So a bit few examples. So you can see that we can do the same thing with different types of skin tone, of makeup color, and it also works well with makeup color that are a bit more eccentric. And also, this is the same example based on eyeshadow, because if you look at the pipeline that I've described, actually, nothing is very specific to makeup. It's not specific to lipstick. So you could actually use that for any kind of augmented reality render that is parameterized by a vector. So here we just use the same thing again on this eye makeup renderer, and show that it's generalized well to this use case. And a little bit of comparison now. So we try to compare our approach compared to standard neural style transfer methods. And if you compare, you see that we managed to reach a high resolution compared to these other methods. And also, when it comes to really unusual lipsticks, like this blue lipstick, for instance, you can see that our model is much more robust. And this is due to the fact that we are basically those samples that are really underrepresented in the data distribution. We don't have really these caveats because we fully control the data distribution, so we can reinforce the diversity. And you can basically draw the same conclusion on this eye makeup. And we're also doing a bit of quantitative evaluation in the papers. So if you're interested in that, I encourage you to read it. And to do that, we use a triplet of ground truth image with an actual picture of some people before and after the makeup. Okay, and talking about real time now. So basically, we know that our renderer can run in real time, but this encoder, we can use a really small model, and actually it works quite well. So this is the inference time on a mobile browser, so using TensorFlow.js on an iPhone. So you can see that the inference can be done in just a few milliseconds. And also keep in mind that you just need to do the inference once. So you take the example image, you estimate the computer graphics vector, and then the computer graphics vector stayed the same throughout the video. You are extracting one makeup, but then you are rendering for each frame. So you just need to run this encoder model once per video. Okay, and to finish, just a few video examples. So you can see that the results are quite stable in terms of we don't have temporal artifacts. They're also, since they are based on computer graphics on a 3D model, there is also a lot of spatial coherence and shine and light coherence across the video. And you can see as well that we did the same thing for makeup. And we have a little level makeup here. Notice, however, that in this case, we just fit the appearance of the makeup, so its color and properties, but not the area of application. Okay, and to finish, in conclusion, what we have presented is a self-supervised framework for learning an inverse graphics encoder in the case where you don't have access to a differentiable renderer. And we showed that it's working well for lipstick and eyeshadow, but I think it could be applied to other augmented reality problems as long as you have access to a parameterized renderer. And to talk about a few limitations, some of the issue with this kind of approach is that actually you don't really know. There is a lot of ambiguity in the source image, so you don't take into account the illuminant and this kind of thing. So you have no real guarantee that your actual product will look the exact same in the end. It's really operation in the apparent space and not in the physical project space. And also, as I mentioned, with this framework, you can extract the area of application for the eye. For instance, you would need to change a bit the definition of this graphics vector if you want to do that. But it should be a straightforward extension. So thank you. That's it for me. I don't know if I'm ahead of schedule or not.
Cool. Yeah, very interesting work. So maybe one quick question. So when you apply your method to a video, do you just apply frame by frame, or do you apply some temporal constraint?
So let me transfer you. Let me jump back a bit in the slides. Okay, so the inference actually look like this. So the encoder, it takes input the reference image, so you just do it once, and then you get the graphics vector. And then the video is generated by the renderer. And the renderer is the piece that I described in the beginning. So it's working frame by frame, but it's a computer graphics method, and usually you have some kind of temporal smoothing inside using optical flow, basically. So there is some kind of temporal coherence that is enforced at the renderer level and not at the encoder level.
Okay,
so
okay, cool.
Basically, the general idea of the paper is that you use a computer graphics things for the generation part, and it has a lot of nice property, and it's a really compact space. So it's simple, but it works well. So
okay, yeah, cool. Yeah. So any other questions from the audience? So if not, let's thank Robin for his great talk. And
thank you.
Yeah, if you have more questions, you can go to Robin's poster in the gallery link later. And so next, let's welcome to our second talk, which is Gaussian controllable image synthesis with 3D Gaussians from unposed silhouettes.
All right, can everybody see my screen?
Yeah.
So hi, I'm Issa. I'm from Brown, and presenting our paper, Gaussian controllable image synthesis with 3D Gaussians from unposed silhouettes. So we've seen a lot of success with generative networks on constrained data sets. We have here the Flickr Faces high quality data set. Pre-process them so that facial features are well aligned across instances, and it's a simple pose to learn, and generative networks work really well with this. But oftentimes, a lot of the data sets that we want to work with are much less constrained. We have here, for example, the Coco giraffe data set, where we see a lot of complex poses of the objects, occlusion of object parts, different backgrounds, and scene composition. So dealing with this type of data is difficult, and there's not a lot of supervision to help us. So we need some sort of intermediate representation to deal with like these complex 3D structures and to constrain our generative network. And we can think of this as an artist mannequin of sorts. We have certain object parts that we can manipulate, and we have this unified 3D framework for our generator to be controlled by. So as input to our method, we have RGB images of the object, as well as mask supervision of silhouettes. And what we're trying to recover, what we're trying to learn and deal with is varying 3D camera pose, object pose, and scene illuminations. So we take as input the mask of the object, and we predict a set of 3D anisotropic Gaussians. And this is our proxy for reconstruction of the input mask. And so once we have this intermediate 3D structure, we can also learn to produce textured images of the object. And we have control over view and pose and shape. So to see our model in action, we have this interface. We can place where the Gaussians are in the background image. We have this global camera rotation, which rotates all the Gaussians together. And then we can also edit the individual Gaussians by scaling, rotating, translating. And we see that our generator follows the shape of that Gaussian proxy. And we can see this again with this synthetic B data set. You can see that the model learns to place Gaussians for the wings, and that the wings follow that position of the Gaussian. So one baseline for our method is Platonic GAN. And what Platonic GAN does is it learns to produce voxel representations per instance. So you give it an input image and it produces a volumetric 3D representation, RGBA voxels, which is then projected using a rendering, a non-learned rendering layer into a 2D image, and that's discriminated on. HoloGAN, somewhat similar method, but instead it learns a deep feature voxel representation of the object class. And during training, it performs random three-dimensional rotations on that voxel space. And the hope is that that rotation is going to map to a 3D rotation for the object in the image. And then it has a projection unit, which learns occlusion. And again, it discriminates on the 2D output. Third baseline for our method is Liao et al.'s paper, in which geometric primitives are inferred, cuboids and spheres, which are then used through a differentiable projection to condition generative networks to produce RGB images, alpha masks, and depth maps so that the objects can be composited onto a separate generated background. So to put this all in summary, for the intermediate 3D representations that we're using for 2D generation, we have voxels where Platonic GAN learns explicit RGBA voxels, while HoloGAN learns like a deep latent space voxel. And then we have quote unquote primitives where Liao et al.'s paper learns to place geometric primitives per object, while our method is Gaussians per object part. So we have control over the object pose, the individual object pose. So to go deeper into our approach, during training, our model learns a canonical set of 3D Gaussians. And then we have per instance, we infer per instance transforms from an input mask, and which are scaling, translation, rotation for the individual Gaussians. And then we also have a global camera rotation value. And we apply these transformation values to our canonical set to produce our per instance 3D Gaussians. These are fed into a differentiable projection function, which produces 2D Gaussians, which then condition our generative network to reconstruct the mask. We also have a self-supervision step, which performs a random rotation on our 3D Gaussians and generates a mask from that randomly rotated Gaussian set and feeds it back into our network to infer 3D Gaussians from that, and then performs the inverse rotation, and we have a loss to make sure that we've recovered our inferred Gaussian set. And so here's a summary of our losses. We have a reconstruction loss between the input mask and the generated mask. We have a loss between the Gaussian densities and the mask, input mask, to make sure that they overlap. And we have a similar loss in our self-supervision step. We have an adversarial loss for our generated masks and a feature matching loss to make sure that we produce detailed, high quality masks. Here's a sample of our synthetic data sets. As you can see, we have a variety of backgrounds and lightings and object poses. Here are some results on mask generation. As you can see, our method is consistent, generates like a consistent shape across the rotations, and is also sharper than the other baseline methods. Hologan struggles in actually like doing a real 3D rotation. The giraffe seems to flip like 180 degrees in the middle of it. Photonic GAN suffers from a lack of resolution, just inherently because of the voxel space that it uses. Liao et al.'s paper suffers from similar effects as Hologan. Here are results on the bee data set. As you can see, the wings of the bee stay put in our method as we rotate, but in Hologan, there seems to be an entangling of the pose of the wings and the rotation of the voxel space. Photonic GAN also, again, suffers from inaccurate shape reconstruction and resolution. So the number of Gaussians in our model is not, it's not chosen by the model, it's a hyperparameter. And we can see that increasing the number of Gaussians helps assist the model in generating like a more consistent shape across rotations. And here are some results on texture generation. As you can see, the lighting remains consistent across the rotation in our method, but in Hologan, as we rotate, we see lighting varying, and similarly with Liao et al.'s. And again, just there are some accuracies with shape estimation with Photonic GAN and Hologan and Liao et al. And the pose of the giraffe is also varying as we rotate. And again, we see similar effects with the bee dataset. Photonic GAN doesn't do a great job with inferring RGB texture. And this is the Pegasus dataset. We see sometimes the Hologan and Liao et al. Fail to produce rotations as you rotate the representation, the intermediate representation. And lastly, to show that our texture generator is conditioned on the background image. And we can see that the texture is appropriately lit to the background image. And we can also modify the latent Z vector for the texture generator to produce different lightings and different appearance within that background context. Yeah, that's all. Thank you for listening.
Yeah, that's very cool work, and thanks for the talk. And any question from the audience? If not, maybe I have a quick question. So what if you say increase the number of Gaussians to an extreme number? Would that give you like super realistic results, or would that collapse the system?
So increasing the number of Gaussians does increase the size of the network, and I mean, too many Gaussians would make it infeasibly large. But it also, like at a certain point, we observe that Gaussians would be thrown out by the network. Basically, the network would shrink down Gaussians and throw them out. Like they would be orbiting the object and basically not contribute to generation. So if there's a superfluous amount of Gaussians, the model will just discard them.
Okay. Cool. I think we are running out of time, but we need to start our poster session, which will be in the gallery room. And for authors, so you can share your screen to people around you and talk about your work. And I will share my screen with the gallery link so that everybody can go there. You can also find it in the CVPR workflow platform.
May I just add one comment? For poster authors, on the website schedule, there is a number next to your poster. If you go and stand by that poster board on Galley, and then for people attending the poster session, if you go and look at the schedule, go and find the number next to the poster that you're interested in, then in Galley, that's where the presenters will be. All right, both links are in the chat to the gallery and then to the website to find the numbers. And the poster session lasts as long as you wish, but we are back here at 1 p.m. Pacific time, 4 p.m. Eastern time for Sergey Tulkov's talk.
Mm-hmm.
So thanks everybody, I'm going to the posters.
Okay, yeah, thanks everyone.
Cool. Let's get started. Welcome everyone to this session of the AI for Content Creation workshop. My name is Kalyan Sunkavalli. I'm a senior research scientist at Adobe Research, and I'm excited to introduce this session where we have 4 talks from invited speakers, fantastic invited speakers that we are excited to hear from. And we'll also have an oral session with 2 talks later in the day. So to kick this session off, we have Sergey Tulyakov, who I'm very excited to introduce. Sergey is a lead research scientist at Snap, where he also heads the creative vision team. He's done a fantastic set of work on using AI and generative adversarial networks for editing and content creation across images, videos, 3D, and a whole spectrum of other visual media. So excited to hear from you, Sergey. So take it away. Thank you.
Hi, do you hear me well? All right.
Yes.
Yeah, I'm also very excited to be here today, and somehow it's lunchtime, so I wanted to make content a little bit more entertaining, but I realized that for many people it's actually not lunchtime, and then I guess this session will be recorded and transmitted again, so for them it might be one different time. So anyway, so thanks for a great introduction, and I will talk today about image outpainting, and we would focus on diverse and high quality image outpainting. So let's dive in. So what is image outpainting? So given an image like that, for example, we would like to arbitrarily extend it to along the 2 dimensions, such as here and here. And there are several key features such extension should conform to. One feature is that it should not be just a straightforward copy of or expansion of the content that is in the source image. And second, it should not contain any scenes or otherwise visible extension artifacts. So there are several works that try to address this problem via image-to-image based formulation. Indeed, you could take your an image, a big image that you have, and you could mask some part of this image. Then you can use the original image as the target, and you could learn the transformation or extension using a convolutional neural network in a image-to-image based manner. So what's the problem? What's the problem with such formulation? So first, the main problem is that image-to-image translation methods, they learn a conditional distribution of the target given the source. And in this task, this conditional distribution and this problem in this framed in this way may be actually bad. Because as you can see here, that the extension is, let's say, just a straightforward extension of the pixels on the boundary. So the network did not generate new content or did not generate that could have been there. It just extended the boundary. In this work, we see that we can change the structure a little bit, but overall the extension is not so interesting. So it's basically some extension of the boundary. And here comes the first work that I wanted to talk about today. So it's maybe some of you had a in and out for lunch. So in and out actually here means that we perform outpainting, which is out, with inversion, which is in, and so therefore we do in and out. And in this work, we're focused on diverse image outpainting. Before we dig into this work, I wanted to introduce this work. Maybe some of you have read this interesting paper, which is a Kokogan. Basically what they do here, they try to generate images by patches. So how to do that? So we sample some latent, then we can specially extend this latent and we can augment each latent with coordinate conditioning. For example, this augmented vector will generate this patch. So we keep the same vector, the same latent, but augment it with a different conditioning and generate another patch. And we can concatenate all these patches and pass through a discriminator and train in the usual adversarial setting. So now imagine that we have a model like that, and let's say we have this patch and we want to outpaint the rest. So if we could only get back and invert this patch to this latent code, the outpainting process could have looked like we just extend this latent arbitrarily in specially and add the proper conditioning, and we can generate a larger image. So I think now we are ready to look into our method. So we indeed would like to leverage the learned unconditional distribution of patches. And as we saw, the conditional distribution for such problem might be not desired. And we want to have diverse outpaintings. So how to do it? So imagine we have a coordinate conditioning generator. So we explore this latent space and we a GAN inversion. This is basically optimization-based inversion. So we can explore the latent space and find some area in that latent space that corresponds to meaningful extensions of that patch. And we would like to find such latents that first reconstruct well the existing patch, and second, that they produce meaningful extension. And this is how we can perform extension. There are two settings here. One is categorical, one is non-categorical, the other one is categorical. Categorical is on the right, non-categorical is on the left. And we'll look through the non-categorical first. So in a similar way as we saw in the Kokogan, we sample a latent, we can project it to the W space and spatially replicate this W space, augment it with coordinate conditioning, generate each patch separately, concatenate, and then we can train a discriminator. So we have a patch-based generator. So now when we have this patch-based generator, we can actually perform inversion. So we use a standard optimization-based method for GAN inversion, and in addition to L1 and perception losses so that the reconstruction works well, we had also a prior loss on this Gaussianized latent space. So we computed the training statistics of W and made sure that the Gaussianized W is this one, lies in this, conforms to that statistics. Additionally, we applied the mode-seeking loss, which worked well for many image-to-image tasks. And as I mentioned before, we would like to have diverse image outpainting results. And how to enforce diversity here in this problem where we actually perform inversion by optimization. So we do it in a way that we sample multiple starting points for optimization, and we, as the optimization converges, we'd like the found W's to be different. So we want them to be dissimilar. We want the reconstruction task to be still done well, but we want the W's be different. So in this way, we could sample different W's and we could generate diverse outpaintings. And now the categorical setting. In the categorical setting, the major difference is that now we have categories for each patch. Categories are one-hot vectors that are, for example, more grass, more water, stuff like that. And we have, again, Z, we project it using the projection network. And then we combine categorical and non-categorical variables together. And the rest of the framework stays the same. So here, combination of categorical, non-categorical. And then additionally to the discriminator, with additional classification laws that the discriminator tries to tell which labels were used to generate this patch. And this is done in a similar way. It's done in the InfoGAN paper, in which they would like to enforce that the generator doesn't skip those inputs. Optimization is performed similarly. We again take the reconstruction, they use the reconstruction and other losses. But when we do outpainting, we further provide the categorical labels for the patches that we want to synthesize. These are the categorical labels. So let's see some results. So this is the input image, and this and these are diverse outpainting results. So we can see here that they are realistic. There are no obvious artifacts on the boundary. They're diverse. So for example, you can see that there is a wave which is not present anywhere else. So there is more rock. There is a stone here, and it's similarly for every other outpainting result. So it's not just a straightforward copy of the content because we didn't have this conditional context and outpaint in a generative way. So then we can also outpaint churches. We could generate diverse towers. We can generate 2, 3 towers that are diverse. And I also would like to show here the importance of prior regularization. So if you remember, we have a reconstruction loss to perform the inversion. But if we focus only on the reconstruction loss, the optimization overfits to reconstruction task. And basically the outpainted regions, they look like the original input image. So it overfits to that task and doesn't consider the outpainting task. But if we compute the prior loss, if we add the prior loss, we see that the boundary disappears and this no longer happens. So you can see that it's much better here. Then finally, we could do outpainting into different directions. We could even support irregular boundaries and stuff like that. And I would also like to show some categorical outpainting results. So we could invert this patch and then categorically extend it to, for example, have more waterfall, more sand, more rock. We could ask to add a tower or a tree here, or like a mountain. So we indeed have some control. If we perform the process several times, we can create longer panoramas. And here, what we do, we take a patch, we generate another patch, then we invert this patch, and so on. So this process is a little bit time consuming. And another implementation detail I would like to share here is that we, so as we do this panorama generation, there could be some boundaries, like some boundaries you see here. So to avoid this or to make them less pronounced, what we do, we generate a patch in between. So since we have coordinate conditioning, we can generate, let's say, this patch and also a patch in between, and we can blend all three patches. And in this way, we get rid of these boundary artifacts. But so these are interesting results, but this idea that we need every time to invert and we cannot generate infinite panorama and there are some boundaries actually led us to consider a more fundamental problem, which I'm going to talk about in a minute. So before we get back to image outpainting, we will look at a different way of generating images, and then we get back to image outpainting again. So I would also like to present the Infinity Gun work. And as you can imagine from the title, it can generate infinite images. And so let's see how it works. So another motivation for this work is that the data that we see in datasets is usually very cropped. It's we don't see large panoramas. This data is very hard to get, and I guess if we filter the datasets and require the images to have high resolution be large, we will end up with few images. So the question that we'd like to address is, can we use these observations and maybe even smaller ones to generate images like that? And obviously these are real images. Again, so let's get back to the idea of the COCO again. And as I recall that there is a common joint of like a global latent that is then specially extended and augmented by the conditioning, and we could generate image patch at a time. So technically we could augment especially even beyond what we learned. And this way we could generate a larger image. The discriminator, however, still needs to use a large image to be trained on, and we will see in later slides that it doesn't work so well. But this is an interesting idea that we decided to explore further. So what is Infinity Gun? So Infinity Gun is a patch-based generative network where the discriminator and the generator are both patch-based. So we can synthesize very large resolution images, one image at a time by parts independently, seamlessly, and with very low memory requirements. For example, all the results that I'm going to show, the models were used to generate them were trained on one Titan X and also tested on one Titan X. So the generator consists of two parts. One is structure synthesizer, one is texture synthesizer. And we have a global latent. We assume that the whole image has some global holistic appearance that can be modeled by the global latent. This global latent is passed to both structure synthesizer and texture synthesizer. And the structure synthesizer is implemented as an implicit function. So we can query structures at any point in space. And for every point, for every queried point, we can sample a different local latent. And local latent is sampled as a Gaussian, from a Gaussian distribution. So given this local latents coordinates, the structure synthesizer can generate local structures. Again, so they're independent. And then the texture synthesizer can generate small patches. And we can query the implicit function and we can generate the local coordinate, the local latents as much as we want. So we can spatially extend them as much as we want. So therefore we can generate actually very large and infinite resolution images. And one thing I wanted to share here is a couple of words about the coordinates. So we see an image like that was generated by this approach. And imagine we want to generate the patch here at this location. So we can see that that here vertically the pixels progress from the rock to some water, then there is some mountain, skyline, and then there is sky. And that's true for every vertical row of pixels. It goes from, let's say, grass, water, rock to the sky. So it saturates at both ends. And therefore, we model it with tan H. So we want, again, so it also want to saturate it at both ends. If we look at the horizontal dimension, we see that there is rock, then there is water, then there is again rock, then there is again water. And this happens with different periods. So you cannot actually say what will be the progression along the X direction, but what you can say for sure that the patterns will repeat. And therefore we path it through periodic functions. And therefore the coordinates are modeled like this triple tan and cosine and sine. For models for images that don't have this bias, like that for images maybe like satellite images, it can be modeled differently. Okay, so the discriminator is trained using real patches. Oh, it's generated patches and also real patches. And additionally, we want the discriminator to be able to tell what is the vertical location of the patch. So we have this auxiliary loss that tells us what's the vertical location of the patch.